How can you see the air? You can't. You will answer, it's transparent. But here's a problem. Probably everybody has seen such a picture on a fine day. Such a slight tremor over the hot earth or road. This is the air heated near the surface, rising. So you can still see it. This vibration of air over a heated surface or a barely perceptible trace from the flame of a candle on a wall is called a shadow method. Light passing through inhomogeneous layers of heated air is refracted in them, and as a result, we see an image, a light shadow. In the 19th century, this method was improved. The French physicist Léon Foucault, in the middle of the 19th century, designed an apparatus for controlling the accuracy of manufacturing lenses and mirrors. He put an opaque screen with a sharp edge in the focus of the mirror. It would then be called Foucault knife edge test. The image was focused at the very tip of the knife, and if there were defects on the surface of the mirror, the light reflected from them was deflected and passed by the edge of the knife, leaving a dark spot on the screen. Later, this method was improved by the German physicist August Doppler, and as a result, a new device was invented which had this rare ability to make video of the air. Here is the device. It is able to distinguish not only inhomogeneous air densities, but different densities in general, water, gases, and the resulting photos and videos are called Schlieren method. But from the point of view of the modern world, is it possible to say that the device is still quite used? Until now, it's a fairly useful device, and here's why. It allows you to see the real phenomenon around the model during the experiment. You can use computational methods to calculate the characteristics of a model. But until you send the model to fly, or don't make an experiment with it, you don't see how it is blown by the flow of air. You cannot confidently say that the computational methods give the right solutions for this model. Usually, the Schlieren method is used to test purely scientific things. For example, the aerodynamic properties of an aircraft. It's a great way to see the airflow around the model airplane in detail. But we decided to use this device to look at everyday household things. And that's what we got. Here's what the simple action of striking a match against a matchbox looks like. You can see the flame too, but the main thing is the air heated by this flame. With the naked eye, you cannot see it. A glass filled with dry ice, the chilled air, is clearly visible, flows down along the sides. Cotton wool on the stand, drenched with acetone. We see how it gradually evaporates and also flows down. A very unusual shot, a balloon pierced with a needle. The escaping air instantly mixes with the air outside in some incredible mess. A normal shot would show, well, just an instantly bursting balloon, without all this air disturbance. Since the soda contains carbon dioxide, you hardly open a bottle that it rushes down. Because CO2 is heavier than air, it's only with the help of the Schlieren method that we can see this clearly. An electric bulb heats the surrounding air. Propane gas from a lighter, and the same gas when it catches fire from a spark. Since the Schlieren method can be used to see different densities of transparent gases or liquids, we can now see what the water looks like when there's an immersion heater put into it. Heated layers of liquid are immediately visualized. And this is glass. It is done roughly. And although it is invisible to the unaided eye, glass is glass. The Schlieren method immediately sees its different densities. It doesn't even seem transparent at all. And finally, this is what the explosion of a firecracker looks like. A burning Bickford safety fuse. And an ordinary hairdryer. After all, the Schlieren method really gives a unique opportunity to make the invisible visible and to look at familiar things from a new and unexpected angle.